Okay, here we are looking at example 4 in the curve sketching notes. Again, we're doing the same thing that we've done in all of them, which is find the coordinates of our relative extrema and our inflection points. Let's take a notice at our function q of t. It is a continuous function. It's defined everywhere, so we can put that in. Q is continuous and differentiable. And we have the reason for that. It is the composition of continuous functions, a parabola and a exponential function. And so we know that our domain is negative infinity to infinity. So we know that we don't have to worry about any critical values where our derivative is undefined. It's only going to be critical values where our derivative is equal to 0. And then our possible points of inflection will be where the second derivative is equal to 0 when we're taking a look at this. All right, so we'll take a look and we'll go ahead and we'll find our first derivative. So q prime of t. Make sure that we pay attention. Since it's composition, you are going to have to use chain rule. So we do our derivative. Derivative of e to the stuff would be e to the stuff times the derivative of the stuff, which is negative 2t. In terms of our critical values for that, we would have q prime of t equals 0. The only factor that affects whether or not the product is going to be 0 is the negative 2t, so that would be at t equal to 0. We can do a real quick sign chart for this one. Fairly straightforward. So we put in our 0. E to any power is always going to be a positive number. So the only thing you have to worry about is the negative 2t, which is a decreasing line. So we know that it's going to be plus 0 and minus for our q prime, which tells us that our function q is going to be increasing and then decreasing. So we're going to have a relative max at x equal to, oops, sorry, it would be helpful if I use the right letter, at t equal to 0, because q prime switched plus 2 minus. Our coordinates for that with 0 and q of 0 would be e to the 4th, and we'll get the decimal value for that later. I basically just plugged in 0 up here for t squared. All right, then we go ahead and now we need to do the second derivative to get our possible inflection points. And our second derivative, taking a look at it, we're going to have to use product rule this time. So I'm going to do the first times the derivative of the second, which is again e to the stuff times the derivative of the stuff, plus your first e to the 4 minus t squared times the derivative of the second, negative 2. And then once we get to here, we do want to go ahead and factor it. I'm going to pull out a negative 2 and an e to the 4t. So negative 2 e to the 4 minus t squared. That's going to leave us with here minus 2t squared. And then over here, we pulled both of them out, so plus 1. All right, then we can pretty much know that our second derivative is going to be equal to 0 when you have, let's just double check, make sure I've got everything here, is going to equal to 0 when this factor is equal to 0. Again, remember this one's not contributing, doesn't equal 0, so we're going to take our negative 2t squared plus 1. We're going to set it equal to 0. You're going to solve. T squared equals 1/2. So t equals plus or minus 1 over root 2, or plus or minus square root of 2 over 2. We're going to take and we're going to complete a sign chart for that one. So negative 1 over root 2 and 1 over root 2. Taking a look at our notation here, this is a flipped parabola, so it would be minus plus minus, but then we have it times a negative, so it's going to end up being plus minus plus. We can plug some values in and check that as well. but that would be the easiest way to do that. So we know that that's our second derivative. So Q, taking a look at it, is going to be concave up, concave down, and concave up. So we're going to have points of inflection at our 1 over square root of 2. I'm going to fill in the y value, and negative 1 over square root of 2 because your second derivative switched signs. All right, and then we would simply plug those values in to the second derivative, and that's just basically plug and chug. Ends up being 4 minus, if you square this, you end up with a half, so it ends up being 3.5. So it ends up being e to the 3.5 on both of these. Okay, and then it does want us to sketch that. And so what I'm going to do is I'm actually going to do this in Desmos because really the whole plotting the points is the first thing that you should do. I'm just going to show you a quick way to check it on your Desmos. All right, so we're going to go to the Desmos, which is right here in my curve sketching. And notice that right here I have 0. Let me make sure this is the right point. Yeah, 0, f of 0, because that one was our maximum. And right here is our decimal value for that, so that we would have that for later. Then we have our 2 points of inflection, so I'm going to turn those on and do the sketch for those. And so that's one thing that we're going to look at in terms of sketching it. And we know whether we're increasing or decreasing, we have our concavity. Now, the one thing that I'm going to do before I actually sketch it, though, is I am going to think about the end behavior of this graph because that is kind of what's happening on the ends is going to be important. This is a exponential function, and so we're going to take a look at the limit as x goes to infinity first of q of t. And again, this is that kind of, you can reason it out. We'll eventually teach L'Hopital's rule, which will give us an extra way to figure this out. But for here, if this is going to infinity, the parabola is going to go to negative infinity, and then e to the negative infinity is going to go to 0. So that's just using our knowledge of parent graphs. And then our limit as x goes to negative infinity of q of t is going to be the exact same thing. Is that when we take a look at it, our negative infinity squared is still going to end up making this minus infinity, so that is also going to go to 0. So we're going to need a horizontal asymptote at y equal to 0. So if we come back over here, and I actually went ahead and already put that in, and you can see the dotted line coming across here. So what we know, if we look back at the information that we have, is that we want to be approaching the horizontal asymptote on the ends. These are points of inflection. We're going to increase until we get to here, decrease after here, and we want to make sure that we change our concavity. And if you check over here on where were we, concave, we start concave up, then down, then up. And so if I was going to sketch that, and I can just kind of do a rough sketch here and then we'll check it, is we would be saying something along the lines of going concave up to here, and then concave down through your max, which kind of missed it a little bit, but that's okay. Then concave down until I get to that one, and then concave up heading along that way. And so that's kind of the shape that we would be looking for, hitting those target points. And then we can check it over here. Let me switch to that and turn it on. And then you can see, what are the things that I've missed? Look, I'm pretty good up here. This part right here should go decreasing pretty quickly to that. But you would check that with your finding some extra values or something. We're kind of getting the basic shape that's there. All right, so that will end this video, and we'll go on to the next example.